Is nano-magnetite the smoking gun that can be used to locate shallow, white hydrogen in the earth? Let's drill and find out. Let me explain. About 20 years ago, I was involved with deepening an existing well in Oklahoma. The well was originally drilled to 5,000 feet and extended to 7,000 feet. The extension was drilled to test the possibility of trapping hydrocarbons in an overturned, recumbent fold. Several porous zones within a thick carbonate section were identified from well logs, and each zone was tested for hydrocarbons by swabbing back formation fluid into the drill pit. The tested zones were determined to be unproductive. When swabbed, each of the tested porous zones would easily give up a very black cloud of salt water that looked like oil upon entering the drill pit. However, given time, the black cloud would settle to the bottom of the drill pit, forming a black layer in the bottom of the drill pit. When the black material was recovered and dried out, a very fine black powder was produced. Because it was attracted by a magnet, it was assumed to be ferromagnetic magnetite particles small enough to move freely in brine-filled, carbonate rock porosity. I had never encountered or even heard of this situation before in my 25 years in the oil patch. Because of my curiosity, I decided to determine the purity of the powder and size of the particles. Using X-ray diffraction, the black powder was shown to be very pure magnetite. Fe3O4. Using a scanning electron microscope, the magnetite particles exhibit an octahedral crystal shape, with sizes ranging from 20 to 50 nanometers. This was a surprising observation. I always thought pure nanoparticles had to be created in a controlled, hyper-clean, laboratory environment. These natural, magnetite nanoparticles are extremely reactive antioxidants. In the presence of 3% hydrogen peroxide and at room temperature, they readily decompose the solution into water and oxygen. These particles can play many different roles in redox chemical reactions. Now that the nanoparticles I recovered from a carbonate rock 20 years ago have been certified in terms of purity, size and redox activity, let's add 20 years of advanced, geochemical research and see how they could possibly play a role in hydrogen exploration. The question as to how magnetite nanoparticles could be formed in the pore space of a carbonate rock was answered in 2006 by a paper entitled Formation of Magnetite Nanoparticles by Thermal Decomposition of Iron-Bearing Carbonates, Implications for the Evidence of Fossil Life on Mars, by Alicia Cohn. In her abstract, she states that the thermal decomposition of iron-bearing carbonates to form magnetite nanoparticles was studied in order to better understand the parameters that control nanoparticle formation. Also, in a secondary electron image, where a cluster of magnetite particles appears white, she states that SEM observations revealed magnetite grains on the surface of the carbonate rather than embedded in the carbonate. This explains the presence of the nano-magnetite in the carbonate porosity. Most likely, there is no preferred magnetic orientation to the particles, consequently, they are weakly held together and could be easily dispersed by fluid motion during swabbing, thus creating the black brine observed at the surface. Finally, the presence of iron in the drilled carbonate was verified using drill cuttings and a strong magnet. The cuttings were attracted when floated on a water raft. The significance of magnetite in the generation of white hydrogen is stated in a recent paper in Frontiers in Earth Science entitled Reassessing the Role of Magnetite During Natural Hydrogen Generation. This slide shows an SEM photograph of nanomagnetite with quotes from this significant research that I would like to read. Starting on the left it states, for the purpose of experiments, gold capsules filled with magnetite powder and H2O were run at 80 degrees centigrade and 200 degrees centigrade. After experimental alteration, high amounts of hydrogen were quantified. On the right, the paper states concerning hydrogen exploration, this work provides evidence that natural hydrogen can be generated at near ambient temperature. These statements lead to the bottom quote which reads, as for the future of native hydrogen exploration, these results demonstrate that magnetite-rich lithologies should be targeted while exploring natural hydrogen resources. In closing, the statement, magnetite-rich, certainly applies to the iron-rich carbonate rock that I drilled into 20 years ago, the formation swab was producing about 10 grams of nano-magnetite per gallon of brine. A very recent article in the University of Texas News dated January 23, 2025 states that producing hydrogen from rocks gains steam as scientists advance new methods. In summary, take an iron-rich rock, add water to it, which produces nano-magnetite in the rock porosity, which in turn generates natural hydrogen gas. Given the extremely low density of the hydrogen, it can then migrate upward and be trapped to form a hydrogen gas reservoir. As I mentioned at the beginning of this presentation, we can test the possibility of using nano-magnetite in the pore water as a smoking gun to help in locating shallow, white hydrogen in the earth. Assuming the well that I participated in was down dip of the actual hydrogen trap. Drilling an up-dip well in the same iron-rich carbonate rock may lead to a hydrogen reservoir. In support of this, I remember the well having a wellhead that was in tubing connection with the iron-rich carbonate/magnetite formation at about 6,800 feet below the surface. I remember visiting the well periodically and opening the valve at the wellhead to see if there was any sound of activity coming from the well. Upon opening the valve, a small amount of flammable gas was produced. Although I never determined the gas composition, this could possibly have been flammable hydrogen. The following slide suggests the possibility of an up-dip location which traps the upward migrating hydrogen. This geologic cross-section displays an eroded, recumbent fold in southern Oklahoma. The iron-rich, carbonate rock that contains magnetite has been folded over to form a structural trap that has been sealed by a thin granite layer. The hydrogen gas that has been generated within the iron carbonate has migrated up-dip to form a reservoir. The down-dip well that I participated in and observed the dispersed nano-magnetite intercepts the iron-rich carbonate at a level below the gas-water contact of the reservoir. The presence of a hydrogen reservoir, sealed in granite, can be tested by drilling an up-dip, 5,000-foot test hole. The top of the granite has been established by shallow and abandoned natural gas wells which stopped drilling upon encountering basement rock. The photographs below the cross-section clearly demonstrate the presence of large, low-lying, recumbent folds in basement granite and metamorphic rock. The exact thickness of the granite cap rock has not been determined, but it is estimated to be several thousand feet or less. I am looking for a company or university to closely work with in order to test this novel hydrogen prospect. I have a doctorate degree in geophysical sciences from the University of Chicago and 20 years exploration experience with Conoco. Financially, I would like to recoup my portion of the dry hole costs in the down-dip well. If interested, please contact me at cancerout@ymail.com. Thank you for your time in viewing this presentation. I would like to add a supporting final comment to this presentation to help persuade you to get involved in this prospect. Being a geophysicist, I am familiar with geophysical methods of exploration. In support of the shallow, hydrogen prospect, I would like to report the presence of a low-density gravity anomaly associated with the prospect. Without giving away the location, the prospect outline on the left is shown in red on a residual Bouguer gravity map indicating the prospect is associated with dense igneous rocks in purple. On the right, the horizontal gradient map, calculated from the gravity data on the left, shows a low-magnitude anomaly within the prospect outline. The gradient data is used to highlight small, lateral changes in rock density like those expected for a shallow, hydrogen reservoir. Finally, reservoir calculations suggest the estimated recoverable reserves to be 53 Bcf.